This talk essentially came about from a conversation I had with my neighbor over the road. We're both members of the Canadian Club of Rome, and he was talking about net zero 2050. And I said to him, I said, look, we're not going to make it. We're just not going to be able to mine enough material to make net zero 2050 possible. And he said, well, give us a talk on that. So a few years ago, I gave a talk to the Canadian Club of Rome. And I've since gathered more and more and more material. And now I've got, this is the short version, I should say. I've now got my full slide deck is 250 slides. It's full of information. And I could talk for 2 hours on this topic, but I've cherry picked things to present to you over the next hour. And so what's the issue? And the issue is that we are currently pumping 42 gigatons of CO2 into the atmosphere. And net zero, the concept of net zero, the aspirational dream is that we drive this to zero by 2050, which is really quite close now. It's only 25 years away. The problem is, despite our best efforts, we're actually pumping more and more CO2 into the atmosphere. A bit of a drop there, 2020, a COVID year. But since then, we've seen constant increases. We're now at 41.6. You're going to see slightly different numbers throughout the talk, and that's because different sources quote different things. But the general trend is all going to be the same, that we're in serious trouble unless we do something right now. The other issue is the population growth. Of course, we're seeing, despite falling birth rates, we're projected to have a population of over 10 billion by 2086. And those 10 billion will all want energy, which a lot of the greenhouse gases come from energy generation, particularly in countries that have previously perhaps been a little bit lower down on the social, the industrial scale. And they want the same things that we have. So there's going to be a growth in energy demand. So most countries have signed up to this aspirational dream of reducing carbon emissions by 2050. And you can see on that wheel there that some countries have already achieved it. Some countries have achieved it. 6 countries have already achieved it. Those in yellow are on course to achieve it by 2030, in orange by 2040, some by 2045, and then the vast bulk by 2050. Some have not yet committed. 3 countries have not yet committed to achieving, but essentially the whole world is committed to reducing carbon emissions. And we've known this for some time. Here's a couple of articles from some years ago that point out that we're not going to be able to get there from here unless we have a lot more mining. So this is a constant theme, and I think the message is beginning to get through. How do we get there? Well, there's a number of different paths that we can take. And there's this wonderful paper that I encourage you to read that was published a few years ago, talking about shared socioeconomic pathways. And they discuss 5 different pathways, of which the 2 end members are what they call SSP1, sustainability, which is taking the green road, which is basically we will achieve net zero by 2050. And these have low challenges to mitigation, but very high challenges to adaptation and high challenges to acceptance. And then there's the fossil fuel development road, taking the fossil fuel highway. You might characterize that as drill, baby, drill. High challenges to mitigation, but low challenges to adaptation because it's continue as is. So what's the consequence of these 2 end members? So here on the left-hand side, you can see the predicted carbon emissions starting from around 40. So this was generated from the IPCC's 6th annual assessment report. And you can see starting around 40. And if we follow the fossil fuel road, if we carry on as is, we are going to more than triple our emissions by the end of the century. However, if we do what we have to do from this point on, we will reduce it to net zero by about 2050. We'll achieve it. So really, we really want to be on this SP1 path rather than SP5. And the consequences of these two paths are shown on the right in terms of global temperature change. Based on a temperature of an average temperature that we saw in 2000, if we follow the green path, SSP1, we should see only a 1 degree change from where we were in 2000. But if we carry on with a fossil fuel development, we'll see a 5 degree increase by the end of this century. And I don't need to tell you what the consequences of that will be. There'll be a lot of glacial melting, but more importantly than glacial melting actually is thermal warming of the oceans. That great big volume will warm. It needs more space when it's slightly warmer. And that's the thing that will cause a huge amount of flooding of cities near to the coast. So in terms of emissions by sector, we find, as I mentioned, that 3/4 of the emissions are coming from the energy sector. It's producing the energy that we need, energy use in industry, in transportation, and in buildings. So let's attack the big problem first: energy generation and transportation. There's some carbon emissions, of course, from agriculture, from waste and industry, but they're a small factor compared to our energy generation. I'm going to be showing a few times through this talk information on the periodic table of elements, just to remind you what the periodic table of elements is like. And there's one example, which is, can I lick it? And I like this one. It shows you elements that you can lick and elements that maybe you shouldn't, and elements you really shouldn't. And elements not at all to lick. And of course, the heavy elements are ones you should be licking. But here's a chart that's produced as of 2017 that shows the critical minerals as defined by the USA, Australia, Japan, and EU at the time. And all these different countries had different definitions of what a critical mineral was. And the color represents how many countries of those 4 consider that particular element a critical mineral. And you can see here that magnesium is all countries, and niobium, all countries consider those a critical mineral. However, since that time, there's been a huge amount of change. And here we are today. And this list now is a concatenation of the list from USA, Australia, Japan, EU, and Canada. And on the new updated list, you can see on the left there are all the elements that are shown in blue on the periodic table on the right. All of those are considered critical minerals. There's 4 that are not on the USA and Australian list yet. Moly, iron, sulfur, and potassium, and phosphorus, sorry. But one thing that really to point out is that now at this point, more than half, well more than half, 2/3 of the periodic table is now comprises what's termed as critical. So what are the challenges that we have to beat to get to net zero 2050? The very first one is the poor social acceptance of mining, and that presents itself in different guises all the time. The second one is the poor public appreciation of the need for a huge amount of mining to achieve net zero. And this, as I said to my neighbor a couple of years ago, he didn't appreciate it. And the poor appreciation actually of the difficulty of such ramping up this involves. And then the third one, and I'm sure you're very sensitive to this in Laurentian, is the reduced enrollments in the earth sciences at Western University. So I'm going to go through each of these in turn. In terms of poor understanding, here's a quote from the UN Secretary General Antonio Guterres that he made at COP26 in November 2021. Enough of treating nature like a toilet, enough of burning and drilling and mining our way deeper. We are digging our own graves. So here we have the leading politician in the world, if you like, And he didn't understand in 2021 just how important mining is in order to achieve our net zero goals. So the unattractiveness of mining, mining is associated with pollution, it's associated with low technology, it's associated with being inconsistent with a modern, clean, high-tech world. And the result of all these is that mineral exploration, geophysics, is an unattractive career. And here on the right, I could pick examples from all over the world, but I thought to pick a Canadian example. This is called the Dirty Dozen, BC's top polluting and risky mines. And their front plate cover on the document is about the Tulsa mine in northwestern BC. And it was only operated for 6 years, a relatively short time. But for the last 70 years, it's been polluting the river that you see there, the Tulsa River. And it's leaking untreated acid mine drainage at an estimated rate of 1 million liters a day of mine drainage that's elevated in cadmium, copper, lead, and zinc. But you've got these stories from all over the world, wherever you go. It doesn't matter which country you go in. And so we have a toxic legacy of mining. And the public, rightly so, are skeptical of mining development. So what metal requirements do we need for the future? And this, in all of my, as I mentioned to Richard before we came online, all of these slides I'm going to make available to Richard. So please don't be busy writing everything down. I'll send the slide deck to Richard. He can distribute it to anyone who wants it. And you'll see everywhere I give references to everything I present. So this is the percentage of metal required in 2050 for clean energy technologies. And just look at those numbers there. They're absolutely huge. 400% increase in cobalt, 150% increase in nickel, and so on. You can go through all of these. They're absolutely huge numbers. And here is an example from the World Bank. It's a bit old now. It's a few years old, but still it makes the point that if we want to hit what they call the 2-degree warming scenario, this is a 2DS, if you like, in IPCC language. If we want to hit less than 2 degrees warming, we are going to have to mine 11 times more aluminium, cobalt, iron, lead, lithium, manganese, and nickel than we do today for lithium-ion batteries. If we only double our mining, then that's in green, we'll hit the 4-degree warming scenario. And that's where we really don't want to go. So we've really got to mine a huge amount of all these metals and minerals if we want to get below 2 degrees warming. And that's for lead-ion batteries. And this is the same chart, but for solar photovoltaics, that you can see that we need to mine 3 times as much aluminium, copper, indium, lead, iron, moly, nickel, silver, and zinc than we're doing today. And if we only mine 1.5 times more than we're mining today, we'll hit the 4-degree scenario. So minerals and metals are in absolutely everything. And this is a nice chart showing you the elements on the periodic table that we've used as technologies increase from the 1700s to today. We're accessing more and more of the periodic table. And this is a very nice diagram that shows the elements on the periodic table that went into the very first generation cell phone. And you can see it was about, what, 1/3 of the periodic table? Well, these all have to be extracted from the earth to make that cell phone. But a modern cell phone, it doesn't use beryllium or lead as the older cell phones do, but it accesses now 3/4 of the periodic table. Modern technologies are far more mineral intensive. And the problem is that many of them are difficult to recycle or cannot be recycled. All those in red have a recycling rate of less than 1%. And that means if you want to get more indium, more gallium, you've got to do more mining, more beryllium, and so on. Those in blue, we can recycle at a pretty decent rate. Lead at 75%, copper at 55 currently, although we're hoping to do better than that. And for example, if you look at your phone, everyone's got a cell phone, and it surprised me when I found this out, but we manufacture 1 billion cell phones a year. And for all of those billion new cell phones, we have to mine everything that's in red. And we'll talk about tantalum later. So some of these are lost in life cycle use. And as you can see here, the scandium, gallium, germanium, selenium, indium, tellurium have got less than a year. If you reuse them, you're only going to be able to use them for a year. Cobalt, lithium, copper and nickel, of course, 45 to 60 years. But even copper has to be replaced. And we'll get onto that when we're talking about the the global power distribution systems. So have a look at a single windmill. And this is the amount of rock that has to be extracted to get the metals and minerals that we need for a single windmill. We need 2 tons of rock to get the rare earth elements. We need 3 tons of rock to get the aluminium that we need. We need almost 5 tons of rock to get the copper we need, and so on. And new mining projects are required to fulfill this demand. The capacity additions are going to be tremendous. Here you see the projected energy capacity additions from 2020 to 2030 in terms of what was projected in 2020 for our increased solar and wind capacity. And you can see that we're about 3 times. But when you put in EVs, you find that those numbers are tiny compared to the capacity power rating of electric cars. And we'll get on to electric cars shortly. We'll talk about them in detail. So the point about electric cars is just how much more copper we need. And I'm going to be talking a lot about copper because a lot of the other things like the lithium that we need for lithium-ion batteries, maybe there's a new battery development and we don't need as much lithium. But whatever we do, if we want to move to renewables technologies, move to the future, we need a lot more copper. And here's an example. In a normal car, you need 9 kilograms of copper. In a hybrid car, about 40 kilograms. And in a battery electric vehicle, about 83 kilograms. So you need almost 10 times as much copper in a battery electric vehicle as you do in a gas-powered car. So how many cars are there? There's about 1.4 billion vehicles on the road today globally, about 1 billion cars and 400 million trucks and buses, roughly a lifetime of 14 years. And so we need 100 million new vehicles a year. And on the right is a chart up to 2020 of the number of cars made each year. And COVID hit in 2020. And I should update that and get a newer one. But you can see for those 100 million new vehicles, we need approximately 50 megatons of copper each year to satisfy our need for EVs. The recycle rate is about 55%, which is already quite efficient. We might be able to increase that a little bit, but not by much. So that means we need each and every year 7 megatons of new copper for all the electric vehicles alone. And as part, this shows the timeline of reaching net zero, various points. And you can see that one of the objectives is that by 2030, it's projected or it's planned that 60% of global car sales will be electric by 2030. And in order to achieve that, we need to be mining 4 megatons more copper than we're mining today, right? So how much are we producing? But let's add up the other needs. You know, the projection is that the copper needs for solar will go from 0.6 to 2 megatons. For onshore wind will double to almost a megaton. The offshore wind will go up to 0.4 megatons. So the total increase in copper over today will go from 1.1 to 3.2. So we need another 2 megatons in order to meet the solar and wind increases. And if we assume a 55% recycling, so there's a megaton. The other thing to point out is that globally we have about 150 megatons of copper in our grid infrastructure. And they have a 40 to 50 year lifetime. And they're coming, some of these are coming to the end of their lifetime. And we need 20 megatons of new copper to replace aging infrastructure by 2030 and the same by 2040. So let's add up all these numbers, right? 7 megatons for EVs, 1 megaton for renewables, 2 megatons at least for grid infrastructure per year. And that means 10 megatons of new copper per annum by 2050. And how much are we producing today? We're producing around 21 megatons of copper. And this is a nice chart showing the increase in copper production. It's gone up sort of linearly, but it has to increase exponentially to meet the forecasted demand. So we're currently mining about 21 megatons. We need to be at 30 megatons by 2035, and we need to be at 40 to 50 megatons by 2050. So we're going to have to mine more copper over the next 25 years than has been mined in all the rest of human history. What are the problems with this? Well, the problems are that over 200 of the major copper mines currently producing copper will reach the end of productive life by 2035. Copper grades are decreasing in the major mines. The major mines in Chile, in the copper porphyries in Chile, the copper grades have gone down by 70% from what they were 2 decades ago. And if we look at how many new projects are there that will bring new copper into market, there's only 36 projects worldwide that will only bring an extra 2 megatons per annum, less than 2 megatons per annum. So we're in serious trouble to meet copper demand. Lithium is just as bleak. And there might be a shift from lithium-ion batteries to lithium-sulfur batteries. And these have a lot of advantages, but actually they need even more lithium. The USGS estimates there's 21 megatons of lithium globally, but we need to find it, we need to mine it. Right, and you can see those charts there. That black one is what we're producing today. And those different colors show different estimates of our need, with the orange one being recycling as much as possible. And the one that's going way up to the sky there is no recycling. And the same with cobalt. We're actually going to be in a serious position from 2025 to about 2040 that we have a huge cobalt deficit. And most of our cobalt currently comes from the DRC, over 2/3 of the global production. And cobalt is not defined as a conflict mineral, but it does have questionable human rights associated with it. Another point that's very important, particularly now, particularly here in Canada, we're getting very sensitive to this, is that we have to have social license when we undertake these mining projects. And this paper published in Nature a couple of years ago points out that of the existing projects that are planned to extract clean energy materials, over 54% of those are on Indigenous lands. And we have to have social license in order to be able to continue working. And here's a story about Colorado. They've got as this article says, it's the dirty secret, Colorado's dirty secret, because a lot of the extraction of the $500 billion mining industry is on land stolen from Indigenous peoples. And there's been a number of moves on this to make sure that we have ethical mining and a certifiable chain of supply. And since 2021, the EU requires supply chain diligence of tantalum. That means it doesn't come from a conflict area. It doesn't fund conflicts. And so this supply chain diligence, we should expand and extend to all metals and minerals. So that just like you do with ethical diamonds, ethical foods. And some companies are part of what's called a Responsible Minerals Initiative, and the European Partnership for Responsible Minerals, the Public-Private Alliance for Responsible Minerals Trade. And you can see them in the bottom left there, all the different initiatives that are globally planned and going forward to try and make sure that we have ethical mining. One significant factor that we're going to have to deal with is supply risk. And the extreme example perhaps is niobium. Over 90% of the world's supply of niobium comes from a single source, comes from a single mine in a single country. And just imagine that Brazil, for whatever reason, decides to throttle or even cut off entirely the supply of niobium to the world. All of these things that we need for our advanced technologies, jet engines, beams and girders for oil and gas rigs, pipelines, superconducting magnets for particles, MRI scanners, all of these will stop being made because we don't have niobium. As it happens, Canada is the second producer of niobium at about 5%, and the rest of the world very little. So this problem of supply risk is really important, especially when you consider one country, and I'm going to be talking about a lot about China's influence here, because to my mind, China is the only country in the world that has been serious about this critical minerals problem for quite some time now, and is working very hard to make sure that the Chinese economy doesn't suffer, and Chinese technology doesn't suffer, and Chinese society doesn't suffer because of lack of critical minerals. If you look at this chart on the bottom, you can see where we got our rare earths from. And up until about 1985, most of these were coming from the USA, with some from other places. And then suddenly China started to produce rare earths. And what happened, by about 2000, the rest of the world became complacent, or you could say lazy. And it says, okay, we got China supplying us, we don't need to do anymore. And so from 2000 to 2010, 2012, China was virtually the sole supplier of rare earths to the world. And since that time, though, countries like Australia and USA have recognized this as a problem and have started to do their own exploitation and exploration of rare earths. But one thing that strikes me is this: when you look about what's the known reserves, and China has known reserves of 44 billion tons of rare earths. Vietnam has 22 billion tons. Brazil has 21 billion tons. What's Canada's known reserves of rare earths? It's less than 1 billion tons. Now, Canada is about the same size as China, about the same landmass. It has the same geology, the same tectonics, has the same cratons, the same Proterozoic belts, all the same sort of geology. Why is our number so low compared to China? And it's because we don't know enough about Canadian geology. We've been complacent. We've not been out there mapping all of Canada to find out what our mineral wealth is. Neodymium now for onshore wind. And here you can see some projections of how we're going to hit the different 4, 2, 4, and 6 degree scenarios. The increased amount of neodymium that we need is huge. We're currently producing 7,000 tons, and we need to ramp that up to 250,000 tons for onshore and 400,000 tons, sorry, for onshore wind and offshore wind. Now, the problem is, of course, that we find a mineralization, and within the mineralization is a mineral resource, and within the mineral resource is the ore resource itself, and that's the bit that's worth mining economically. I mean, eventually, if the ore becomes expensive enough, if copper rises, then the ore reserve portion becomes larger, it eats into the mineral resource because it becomes economically worthwhile to take more and more out from the mineral resource. One problem is that currently, over about 3,000 discoveries, only one ever makes it to a mine. And here's an example for copper, showing you one issue. It's a huge issue, and that is the time it takes to go from discovery to mine. And those colored lines on the bottom right there, they show how many copper showings made it to mine and the gradient that it took. And so deposits that were found in the 1950s, 65% of them came to mine by now. And within about 20 years, 40% of them were at the mining stage. But today, for the 2010s to 2024, only 5% of discoveries are making it to mine within 15 years. And so we're having a serious problem that it now takes, on average, 17 years to go from discovery to mine, and far fewer make it. The world is another example of world copper production, and you can find lots of these in different different publications. And this shows an example of how much copper we'll need by the end of the century, with a minimum estimate of 50 and a maximum estimate of 65 megatons a year. And remember that we're currently producing something like 20. So our need for copper is absolutely huge. And on the right-hand side, you can see a projection of what we need. The baseline is carrying on as we are, if you like. And then that net zero line is the huge increase in order to meet the copper needs for 2050. It's been projected that we need to find something like 200 new large to super large to world-class copper deposits and bring them to mine very quickly to meet net zero goals by 2050. The problem is the discovery rate is decreasing. This is a plot showing the discovery rate of gold, uranium, base metals, and others. So if you look at the green, which copper comes under base metal, of course, you can see that we're discovering almost nothing anymore. We're not finding new deposits very fast. And the discovery space is getting deeper. Those green circles there, spheres, they represent the size of the sphere, represents the size of the deposit that was found. The place on that timing chart shows you when they were found, and their position in depth shows you at what depth they were found. And you can see that we're having to go deeper and deeper now for our copper. And we're finding smaller and smaller deposits. You know, virtually gone are the times when we find a huge copper deposit at surface. We know where to go. We know what tectonics does for us. We know, based on these firmly established tectonic models, where we get our VMSs, where we get our iron oxide copper gold deposits, where we get our orogenic gold. So we know this. We know the tectonics, right? So the idea is that you map the tectonics at the regional scale and then focus in at the local scale. And this is a couple of examples of maps of IOCG deposits in Australia from Hogarth 2020, just to show that these big deposits, they're actually lying on the edges of cratons predominantly. You don't tend to get them in the middle of cratons because the craton is so thick that the flux in fluids are not getting up from the asthenosphere through the thickened lithosphere. They're actually coming up around the sides of the cratons, and we're seeing them on the sides of deposits. One wonderful example, I couldn't give you a talk without including at least one example of magnetotellurics, which is my field. Here's an example from Australia, and you might have seen this image. It's perhaps the most famous MT image right now in the world. This is the fingers of God from Graham Heinzen, and they did a mapping over the Olympic Dam, and they were able to image a lower crustal deposit, a lower crustal conducting zone that seemed to have these three fingers coming up. The main finger coming up to Olympic Dam, which is one of the world-class iron oxide copper gold deposits, and fingers coming up to the south and to the north of Olympic Dam to Wordawell and to Vulcan. And these at this time are not economic deposits, but Graham Hansen has done some more work on Vulcan and found a very large conductive anomaly that might prove useful. So the final problem is people, and that mineral deposits are getting harder to find. So we need geoscientists with skills to look deeper. Masters and PhD geophysicists. I'm a geophysicist, so I have that bias, but I think we need masters and PhD geophysicists with strong geology and data science backgrounds. The nice thing about the geosciences is the low unemployment rate. You know, there's virtually not an unemployed geophysicist on the planet, or if they are unemployed, it's not for long. And especially into the future. The income is decent. On the right there, you can see average income of geophysicists, 108,000 for men and 101,000 for women. So we almost have gender parity, which is very nice. One problem is the age profile. And on the left there, what you're looking at in that bar, in that chart, is the age of the members of the Society of Exploration Geophysicists. And over half of the members are over 55 years old. So we're an aging profession, and we're not attracting young people into geophysics, so into earth sciences generally, into geophysics, especially into exploration geophysics in particular. And this global trend for lower enrollments in the sciences, you'll see that across the world. This chart shows the enrollments in undergraduate geoscience in Australia, United Kingdom, United States, and you can see how they've dropped to 2/3 the numbers they were at the peak. And the American Geosciences Institute has projected that by 2030, which is only 5 years away, that in the US alone, there's going to be a talent deficit of around 130,000 positions, because we just don't have enough geoscientists coming into the universities to be trained, and we don't have enough people at the universities training exploration geoscientists. China is the one anomaly, is the one difference. They've done some wonderful things. They've already met their 2030 wind and solar targets. They met them in July 2024. They generate more power in 1 month in last May last year than the world did in the whole year. So China has put a huge amount of effort into getting away from fossil fuel development and fossil fuel generation, energy generation. One problem, and this has been in the news a lot, we're seeing a little bit of relaxing now after Trump went and talked to Xi, is that China has imposed strict export controls on certain of its metals and minerals: germanium, gallium, graphite, and antimony, as of a year ago. And as William Clark in the Mining Journal said last year, Western jurisdictions such as the EU and the US have suddenly realized the advantages of having an industrial strategy. Now, China has got a lock, you might call it a stranglehold if you like, on both the supply and the processing of all sorts of metals and minerals we need for the energy transition. They control 41% of the world's cobalt, 28% lithium, and so on. And in terms of the processing, 95% of the world's manganese is processed in China, 73% of the world's cobalt, 70% of the world's graphite, and so on. What's China been doing about this? Well, One project you might have heard of is Sinoprobe. And this is an academic project, but with very firm industry goal, which is to map the mineral resources of mainland China. And they had a phase one, which is 500 million, which is very successful. And based on that, the head of Sinoprobe, Professor Dong Shuen, was asked to put in a proposal for phase two. And I happened to be in China just on the day he was going to the highest level board of the Chinese government to make a case for a renewal of the Sinoprobe at a level of 40 billion yuan, which is something like 7.5 billion Canadian dollars. He was told it was too small. And he put in a proposal for 65 billion yuan, which is 12 billion Canadian. It was funded. And that works out to about $9 a person. Now, what the earth sciences have done successfully in China is raised the earth sciences to the same level as space science and as the health sciences. It's become a critical issue as China. It's been recognized as such, and now it's being funded appropriately. The other thing that China is doing to ensure its access to critical minerals is buying up mines worldwide. In 2005, China controlled 7 mines outside its borders. And by 2018, that's only 13 years later, that had increased to 60 mines. And the latest number is about 90 mines outside its border. So what's Canada doing? Well, I do like this announcement of a few years ago where Ottawa ordered Canadian companies to exit 3 lithium mines. Canada wants to have control of access to these things, which is very nice. But apart from that, you know, China's dominating. Look how much steel. See this steel production chart. How much we almost got nothing from China in the 1990s, and since then, most of the world's, over half the world's steel is produced in China. Some companies are beginning to make sure that the minerals and metals that they use are ethical. And as you'll see on the bottom left there, Volvo will only use steel produced by renewable energy sources for all of its vehicles from this year onwards. So there is, you know, we see these lights. What has Australia done? Well, Australia, on the basis of the Olympic dam result, Australia has gone ahead and has started a project called Uncover, which is to understand its mineral wealth below its regolith. Australia, of course, didn't have a glaciation recently, so all its mineral wealth lies below 100 to 300 meters of conducting regolith. And so here, Australia is a place where geophysics is absolutely necessary. And as part of Uncover, there's a program called OSLAMP, which is putting in long period magnetotelluric sites, all those dots, in order to map Australia at depth down to the lithosphere's thinnest boundary. And the mapping is about 3/4 finished. There's also a regional airborne EM survey and an Australian EM survey. And this is all part of a 225 million Exploring for the Future program. Well, ironically, though, what's happening in Australia is that despite this, Australia's GDP relying heavily on its mineral wealth, they are closing down a science department, so closing down courses. You will have heard perhaps that McGill University closed its earth science department down. Wollongong University closed its earth science department down. Rhodes closed its earth science department down. Other universities are closing down courses or reducing courses. And this is all because the low enrollment. So it's a vicious circle, right? There's low enrollment, so the courses go, so then you don't get people trained in the earth sciences. And this, to me, is the failure of the university system. Universities need to collaborate nationally about a national program to provide and educate earth sciences within their universities. Canada, we're doing a lot of talking, but not a lot of action. We've got the same geology as the other countries are exploiting. And this article from Northern Miner keeps pointing out that we have the right ingredients to be an EV battery leader. Have a look at the top companies that are working worldwide. And there's very few are Canadian companies. And the Canadian companies have been bought up, of course. Falcon Bridge was bought up by Extracta, was bought up by the French company Glencore. Incos was bought up by the Brazilian company Vale. And so we have no mining national focus or effort. And there's no major Canadian mining company for net zero metals on that list of major mining companies worldwide. And these are the leading producers of various metals. Why are we not on that list? We are on that list for niobium. We're the second leading producer, but we're not producing anything. And you can see how China dominates for a leading producer for most of these. We're nowhere on this league table. And if we don't do something and do it soon, we'll be importing metals from others. And we'll be at the mercy of them for access and pricing. This is a map that you can get from the USGS, which is a list of known major deposits in North America. That's Mexico, US, and Canada. And just have a look how bleak it looks. We know far too little about most of Canada. We're missing out on huge opportunities. And some years ago, the head of Robin Denholm, the head of Tesla, she spoke at the Minerals Council Australia's Mineral Week, and that she said Australia is the only country in the world with resources in all three critical battery metals. Well, that's absolute nonsense. Canada's rich in lithium, graphite, nickel, cobalt, aluminium, and manganese. And Tesla is going to Australia because the geology is better known and the country is mining friendly. So what do we need to do? At the national level, we need a national plan for minerals extraction in Canada. We need a national commitment that no minerals will come into Canada except those that are certified by the Responsible Minerals Initiative. We need a national coordinated strategy to map the whole of Canada at a regional scale using deep crust and mantle imaging, geophysical and geochemical methods to emulate Sinoprobe, Uncover, and US Array. I think there's little sense in sending out geological mapping groups to map small regions. We need to know the whole of Canada first. So we need a national strategy for training modern holistic geoscientists who are comfortable with geophysics, so with physics, chemistry, geology. Universities are where geoscientists are trained, but earth science programs are under threat everywhere due to low enrollments. And each university is an island unto itself. We really need the universities to coordinate. We don't need a lot of geoscientists, but we need enough, and we're just not getting enough trained today. We also need coordination at the national level of a number of our societies. Just look at that list of societies across Canada. Canadian Exploration Geophysics Society, BC Geophysics Society, Canadian Society of Exploration Geophysicists, Geoscientists Canada, Canadian Federation of Earth Scientists, and so on and so on and so on. Why don't we just have one coordinating body? There's just too many people in this game. So the conclusions and the path forward. Some of these issues and some of the numbers I've presented to you will change over time. For example, I didn't have time to show you, but there's evolving other battery types than lithium ion. Some of them actually take more space, and they might be useful as battery walls, but you wouldn't want to put them in your vehicle. But whatever it is, all of these will need to increase mining. There's no path to net zero without a lot more mining. We need to find a huge number of new deposits and find them very quickly if we're to achieve net zero 2050. and if we are to continue our technological advances without a severe throttling of our progress. All the easy to find deposits have been found and are being exploited. So now we have to find deposits in hard places, hard because of geography, politics, or because of isolation and depth. But these should be close to market. Something like 5% of our carbon emissions is due to shipping ore around the world. The drive to net zero cannot come at the cost of environmental degradation or human rights abuses. And I believe that earth scientists and mining companies, we have to engage with politicians. I was recently in the EU at the EAGE meeting in Naples, and I heard about the EU statements about how they want to achieve net zero. And what the politicians are saying was totally unachievable. And it makes nonsense when a politician says something that you know is never going to be achieved. We need to show that mining is essential and that we can do it environmentally sensitively and with social license, especially with regard to Indigenous rights. Thank you very much.
Good. Thank you very much, Alan. That was an excellent talk. Lots of things to think and to worry about, and lots of things to do as well.
Yeah, exactly.
Does anyone have any questions or comments? You could raise your hand, or you could type something into the chat, or unmute your microphone. I have an observation. When I was younger, our family used to get a newspaper, and the whole family would sort of glance through the newspaper at some point, mostly the parents. But as they would flip through, you'd get to the job ads, and the job ads would often list all the different types of companies that were hiring. And when I was growing up, mining companies would often be in that position. And everybody would know about that. And so the parents would say to the children, oh, look, mining companies are hiring, why don't you consider earth sciences? But now, I don't know, you don't get job ads for mining companies unless you are already in the field, sort of thing. What do you call it? The algorithms don't send something to you unless you're already there. Yes. So it's a little bit of a problem, that.
Yeah, and also they want to. I see very few ads that are looking for entry-level people. They all seem to want people with experience.
Yeah, that's right.
Yeah, but I think I think it starts a bit earlier than then. I think it starts in the schools. And for example, when I was in Dublin, I'd heard about this program called Seismology in Schools, and this was a program started in the US. And it was brought into the UK, and I brought it into Ireland. And the idea with seismology in schools is to have a simple seismometer that you put into a school, and the kids learn about the Earth from watching the seismometer. And we bought, I think, 50 of them, and we put 25 in primary schools and 25 in secondary schools. And so we've got, 50 schools where kids are getting exposed to the earth sciences in a real hands-on way. And I think programs like that are essential. And I think you and I, Richard, and other people, we need to be going into the schools and talking about the earth sciences and talking about, pointing out this type of thing, just how important mining is for the future, and making people understand that I've spent quite a bit of my career sitting next to astrophysicists in Dublin. The institute was astrophysicists and geophysicists. And the problems we have to solve in geophysics are just as intellectually challenging and just as interesting as they are in astrophysics. And yet somehow, kids are more drawn into astrophysics than they are into geophysics, because they think it's old technology, whereas the challenges are really tough intellectual challenges.
Yeah, it's interesting. I got in touch with a school teacher I know who used to be a geophysicist, and I said, I'd like to come to our school and give a talk about it. And he says, well, I could do that myself. So if you know somebody that's an entree into the schools, then they're not necessarily an entree because they feel like they can do your job. Whereas to find somebody that doesn't know about it, so it's really hard to do. And often they're too busy as well, too. I contacted a few different schools a few years back, trying to go and talk to them, but they just don't get back to you, right?
Well, earth science in most schools is basically physical geography, right? We really don't teach proper earth science in schools. Great. Well, thanks everybody again for listening to me for the last hour. And as I said earlier on, I'm very happy to share this slide deck with Richard, and anyone who wants a copy of it, feel free to ask Richard for it. Anyone who wants to interact and discuss with me, then please feel free to contact me. And again, I want to emphasize that it's a fast-changing field in terms of the numbers. I've presented you with a load of numbers, and those numbers will change, but what won't change is the need. And I particularly focused on copper because it doesn't matter whether we have different battery technologies or which way we go, we're going to need a huge amount of copper, whichever way we go with in the future, whichever of the new renewable technologies we advance most.
Yes, good. Thanks very much, Alan. I realize you have to go around now, so thanks for joining us. You'll notice I've put in the chat for the people that are still here that the AGU has requested I circulate the link for a poll because they want some feedback on the talk. So if you go to the chat, I won't stop the meeting for a little while. So if people want to stay online and copy and paste that chat in, then they can do so.
I'm giving this exact same talk at the University of Ottawa in 2 days. So if anyone has noticed something that seriously needs addressing and correcting, I'd appreciate it if you'd let me know.
Yeah. All right. Well, there are lots of people that are saying thanks for the presentation.
Yeah, I see.
Yeah.
Thank you. Thanks, everybody. Thank you. I appreciate that. Okay. Bye, everyone. Bye, Richard.
Bye.